All right, let's dive right into this explainer. Look, if you're a support engineer, you absolutely know the dread of troubleshooting data anomalies using slow, resource-heavy subqueries. We've all been there, right? Staring at a screen while a correlated subquery just chugs through a massive payments table, locking up resources and completely testing our patience. But today, we're going to look at a seriously elegant, high-performance solution that completely changed the game in MySQL 8, window functions.
So here's the game plan. We'll start with a quick intro to window functions, then move into ranking transactions, do a little time travel with lag and lead, and then tackle running totals. Finally, we'll bring it all together with a real-world scenario, troubleshooting duplicate charges.
Section 1. Intro to window functions. It's all about speed and elegance here.
I've got to ask, are you still using self-joins for running totals? Because if you are, hey, no judgment, I completely feel your pain. In legacy database architectures, joining a table to itself to calculate a cumulative sum means you're dealing with quadratic time complexity. And as your dataset grows, your query performance degrades exponentially. It's an absolute performance killer on large-scale data. So getting a handle on this basic definition is absolutely crucial. Windowing is basically executing calculations across related query rows while maintaining individual record identities, all without collapsing the result set. Think of it like a sliding window of data. Unlike a standard group by statement, the one that aggregates your data and squashes multiple rows into a single output, a window function performs just a single pass over your data. It simply appends the calculated value right next to your original uncollapsed row.
Just look at the sheer wall of text required for a legacy correlated subquery, especially when you compare it to an elegant one-line window function. It's night and day. Not only do window functions process data in a highly efficient single pass, but the immediate readability gains are massive. Trust me, your future self, and definitely your teammates, will thank you when you're debugging at 2 a.m.
Okay, let's talk syntax. Imagine we're zooming right into MySQL Workbench for a second. The absolute mandatory component of any window function is the over clause. Without it, well, you're just writing a standard aggregate function. The over clause is essentially the magic wand that tells the MySQL engine, hey, I want to perform this specific calculation over a very specific window of data.
Let's break down how we actually control that magic wand. The over clause has three core components. First up, partition by, which logically groups your rows together, like, say, grouping by user or department, but without collapsing them. Second, order by, which dictates the sequence of the rows within that partition. And third, the frame, which sets the exact physical or logical bounds of your sliding window. You basically mix and match these to give the database engine its exact marching orders for that single pass.
Moving on to Section 2, ranking transactions, row_number and rank.
Check out how identical values get scored differently depending on the function you use. Say we have two rows tied at a value of 500. Row number assigns a strict deterministic sequence 1, 2, 3, 4. It literally doesn't care about ties at all. But if you need to acknowledge those ties, like maybe for performance tiers, you'd use rank, which scores them 1, 2, 2, 4, essentially skipping that third spot. Dense rank, on the other hand, also scores them 1, 2, 2, but it doesn't skip the next integer, so it gives the final row a rank of 3. You basically choose the function based purely on how you want to handle your ties.
Say you're working with a sample transactions table. Here is a super common requirement. You need to retrieve only the most recent or first transaction per user. By partitioning by user and ordering by date descending, ROW number assigns a 1 to the newest transaction. Now, quick caveat here, window functions can't actually be used directly in a where clause. So, actually, it's an easy fix. You just wrap this beautiful line of code in a common table expression, or CTE, and then filter your outer query where the row number equals 1. Boom, done.
All right, Section 3, time travel, lag, and lead. Sounds cool, right?
Honestly, lag and lead are revolutionary. They allow your query to literally look backwards or forwards. You can access previous or following rows within a partition to compare sequential data. So if you ever need to compare a user's current payment to their immediately preceding payment, you don't need some convoluted join anymore. You literally just ask the engine to look one row up.
So looking at this example, lag, revenue, 1. Looks exactly one row back based on the chronological order of the months. In financial data analysis, this is exactly how you calculate month-over-month growth or how you quickly spot sudden transaction spikes. You're just subtracting the lagged value from the current value on the exact same row. It is fast and it is incredibly readable right inside your workbench.
Next up, Section 4, running totals using sum over.
To get a really accurate running total of daily transaction volume, you use sum as your window function. But check out the explicit frame specification in the over clause, rows between unbounded preceding and current row. This explicitly tells MySQL to add up everything from the very first row of the partition right up to the row we are currently sitting on.
Okay, huge red flag here. I need to point out a very common pitfall. If you just use order by date without specifying the frame, MySQL defaults to range mode, and range mode groups tied values together as peers. So if two transactions happen on the exact same date, they'll both show the identical combined total. If you want predictable, strict, row-by-row accumulation, you should always explicitly define your frame using rows mode.
Which brings us to Section 5, the real scenario, troubleshooting duplicate charges. As we know from the material, gaps in sequential data or redundant records in a high-volume payments table represent a severe data integrity issue. Imagine we've got a massive table, users are complaining, and we need to accurately isolate the exact rows where the duplication occurred, and we need to do it right now.
So how does a senior engineer tackle this using window functions? Well, step 1, we partition the data by user ID and the transaction amount. This isolates charges of the exact same price for the exact same user. Step 2, we order those partitions by their creation timestamp, ensuring we track charges happening within the exact same minute. And step 3, we apply row number. The first valid charge gets a 1. Any redundant charge that follows immediately after gets a 2 or maybe a 3. So we simply filter for any row number greater than 1.
And here's what that final query structure looks like. By wrapping our window function in a subquery or CTE, we elegantly trap those duplicates. If a user was charged $50 3 times in the same minute, the first charge gets row number 1 and is totally safe. The duplicates get row numbers 2 and 3, they get caught by our where rn greater than 1 filter and can now be isolated for refunds or deletion.
But the absolute beauty of this? The performance. Big O of N. We just solved a critical support ticket in a single linear pass over the data. We entirely avoided the quadratic time complexity and the database locks that a legacy self-join would have absolutely triggered on a table with millions of rows.
So I'm going to leave you with this question. What other clunky self-joins are hiding in your legacy codebase, just waiting to be refactored? Now that you know the power of partition by, lag, lead, and strict row frames, you've got the tools to make your analytical queries faster, cleaner, and far more elegant. Open up MySQL Workbench, find a messy self-join, and try replacing it with a window function today. Thanks so much for joining me on this explainer, and happy querying.